All right, so how you guys doing today? Doing good? Okay. So we have an exam next week. I mean, a week from today, Wednesday, and also the Friday. Soon mostly in a Wednesday part. But here's one thing I want to tell you, okay? I want you to remember this one. So exam 2 will cover chapter 16, 17, skipping 18, 19, and then that's it. Okay, so we're gonna cover just 3 chapters for exam 2. Okay, so that means that I'm gonna finish up the chapter 19, and then we're gonna have a review on Friday and this coming Monday. Okay, before exam 2. So I'll probably put this in the campus today anyway, but I want you to remember this one. Exam 2 covers chapter 16, 17, not 18, and 19. So 3 chapters, okay? So yeah, that's it, okay? All right. Okay, so let's move on to the last part of the chapter 19. Okay, so this is what we're gonna do for the last part of chapter 19 is what we call phosphorus elite addition. Okay, what we're gonna do with this one is whenever you have a carbonyl groups. Should be in your ketone or aldehyde. Okay, so you have a common group over there. What we're gonna do is we're gonna break this one with the A lead. It looks like this. So that looks like phosphorus here. And the phenol groups. That's the phosphorus. Over here, and there's some carbon HR. So what I mean by that is it has maybe this form, and then most importantly, it has a negative charge on this carbon here. So it's carbanium. And obviously the phosphorus only has 4, so it's a positively charged. Okay? So it can do either, so this is they can do resonance with this form too. So just plus a negative here. But when you have this one here, right? You can do this one as well. So they're same thing, but in the resonance form. Either they can do double bond here or just plus a negative charge with the lone pair on carbon here. So this one. All right. So the way we can make this one is whenever you have a triphenylphosphine, there's a lone pair in here can attack the one of the carbon. With the halogen groups, maybe it's maybe bromine here. This is bromomethane, and then there will be. This will make a leave here. Okay, and then you can treat it with the lithium, butyl lithium, and the tetrahydrofurands. They're actually going to have the hydrogen will be taken by this one, and then they leave a lone pair there. Okay. Looks like this. This is how you can prepare for the elite, just using the triphenyl phosphine with the halogenated methyl or other R groups. We can have an elite over here. So normally what we're gonna do is this is too big to write, so I'm gonna abbreviate this part as a Spanish group, which I'm gonna put pH. So I'm gonna write in this way. P, this is the phosphorus, PH is a family group 3. Okay. Positive charge with carbon HR. Could be 2H, 1H, 1R, either way. Okay, and this is a negative charge. Okay, so I can either write this one this way, or I can show you. It's the same thing. Okay, so don't be confused on the exam. Either you're gonna see this one with the same. It's just the resonance form back and forth. It could be anything. Any one of this is okay too. Okay. Does it make sense? So, all right. So if that is the case, what happens to this one is obviously they can do this one and this one, okay? Because this is the double bond, and it can be easily attacked. The one is positive, or either it's double bond coming to here, or the lone pair coming to this carbon, because it's electron poor carbon here. So what it does is actually they're gonna form this one. So I'll show you this one over here. Okay. So eventually they're going to this intermediate state, and then what it does is this goes to here, and this goes to here. So this will become triphenylene phosphine oxide. So it looks like this one. Okay. Now there is one double bond. Okay. So let's just go to this one. So this is the what happens when you do the phosphoryl addition. Actually, this is also called Wittig reactions. Do you guys speak? Anyone can speak German? It's actually pronounced like Wittig. I don't know why, but anyway. So this is something you can do with the Wittig reaction here. So let me show you one example here. Okay, if you try to do, okay, this is one ketone, cyclohexanone here, right? You can treat it with the, maybe just, okay, over here. Oh, just try it. And then what you can do is this is some trick you can do. So whenever you have carbonyl groups on ketone or aldehyde, just switch this one to the R group part here. So I'm gonna put the carbon here with the 2 hydrogen here, so like this. Okay. So maybe you can say on the exam it just looks like this. Okay, yeah. So maybe can you guys try this one real quick? Maybe if you have this one, okay, and then I'm gonna change this one to 1R here, 1R and 1H, and maybe you can try this one. 1 or 2 minutes. So the trick is try to find where the carbonyl groups, and then try to replace that oxygen in the carbonyl group with this R group here, okay? And then that will be just it. Okay. Okay, yeah. So yeah, so let's try to do this together. So we have a carbonyl group here, right? I'm gonna switch that one to this carbon here that has one hydrogen, one methyl group. Looks like this, okay? So if you redraw this one again, what it looks like. Make sense, right? Yeah. Can you try one more? Let's try one more. How about we do? Try to do. This one. About 30 seconds, we'll do this. Okay, so yeah, if you look at this one over here, I'm just gonna replace this one with a carbon and H2, H2. So we'll do this like this. Okay, so perfect. Yeah, I think we're good, right? All right. So let's move on to the next one. The next one is what we call the alpha beta unsaturated aldehyde ketone nucleophilic addition. So what I mean by the alpha and beta is this is how we number or point the carbon near the functional groups. So obviously they share the same functional group in aldehyde, and ketone is a carbonyl group again. So if you have, we've been talking about this one, a nucleophilic addition here. So we have this one comes into electron poor carbon in the carbonyl groups, and one of the pair of electron and the pi or electrons will go in here. So this will be gone, and this will be negatively charged. Okay, so once it's bound to a nucleophile to the carbon, it becomes a single bond and goes to the oxygen as a form of a lone pair. And then later, if you treat with the acidic conditions, they can grab this one of the proton from this hydronium cation, and then they're just neutral now in this one. Okay, so basically what we've been talking most part of chapter 19 was this one. Okay, but there's exception though. There's some weird thing happens if you have alpha beta carbons are unsaturated. So what I mean by that is besides this regular case, if you have carbonyl groups, and also you have here's the carbon here. Okay. If you have this type of thing, okay, so what happens to here is the nuclear file, either negative charge or neutral, or we normally have the one with the charge, but when they do this, they're not attacking here, but attacking here. So this is the carbonyl groups, which have a functional group. So one carbon away from the functional group is what we call alpha carbon. This is beta carbon. So, or even further will be gamma or so on. Okay, so alpha and beta over here. Sorry. So then if you see those two carbons are in a double bond, obviously it's unsaturated. So we call this alpha beta unsaturated addition here. So anyway, so in this case, they're not going to attack here. Okay, they're attacking here in this position here. So then when it bonds to that beta carbon, okay, and this will make a push, right? This is not 5, it make a push to here. This goes to here, right? So this will be single bond now, and this the double bond. So obviously this doesn't look right, double bond on the angle position now. So this will push this one to there, okay? So this one, this there, okay? And then once again, they can try to grab this one again here, okay? So maybe this will become this one, but later they can be taken by other water or base, so they can actually get this one goes to here. Then now it becomes double bond again. Okay? And then this will also push this one to this carbon here because it can go back to here again. So now this will become this is where you can have a lone pair with a negative charge, and they grab the proton. They grab a proton later, so you have addition on here eventually. Okay. So in this case, you're actually going to have addition on these two carbons, alpha and beta. Sometimes people call this the 1,4 addition because as you saw, initially the hydrogen captured by this oxygen would be 1, 2, 3, 4, so 1, 4. But later, eventually, they want to keep the stable carbonyl groups here again. That makes this alpha carbons should be carbanion. Then the lone pair will grab the protons, so it will be addition on these two. Okay. Does it make sense? Okay. So here's the thing. Why does it matter that we have the alpha and beta is unsaturated? So the thing is, it's quite similar to what we learned from alytic position, that you have a carbon. Only difference is you have an oxygen here instead of carbon here. So this is somewhat what? Do you guys remember the conjugate compound? Double bond, single bond, double bond, single bond. They can be well conjugated. Okay. So, but this is a bit different because of the oxygen here. But those three, because of here, they can be kind of somewhat delocalized again, because they have kind of share similar p orbital cloud on all over this 3 carbons over here. So it doesn't make only this carbon electron poor by this one, but all 3. But this is a better position to be attacked on the end for nucleophile. So it goes to the like a movement of the pair I showed you before, because it's all well conjugate with here. So eventually they're ending up putting the hydrogen here in the alpha position when they are attacked by nucleophile on the beta carbon. Okay, that is why. So if you don't have a double bond, it could have been totally different story. Just here, and that was it. Okay, so let's do some problem here. If you have this one over here, okay, and then you can try to treat it with the primary amine, methylamine. For example, methylamine. Okay, this is the primary amine, right? So do you guys remember this? They will form imine, right? So the trick is you're gonna have this one. Okay, this is imine. This is what we learned on Monday, right? Monday. Okay. But let's change the condition here. Okay. Let's say we have this one. Maybe you can try this one real quick. Thinking about the alpha beta addition here. So I changed this one to the double bond, these two. So you can have alpha and beta position. Okay, so yeah. This one. Because of the alpha beta uncentrated nucleophilic addition. Okay. So this it kind of explains it. So if it were just a regular ketone, it could have been just imine formation. But because of this conjugation here, the localized electron, it can actually is on here. So you'll be okay. All right. Let me actually give you. One more. You want to try one more actually? Okay, let's try one more. Okay. Let's try to do the same thing. Method line. Okay. See what it is. So obviously we're not from imine anymore because of this conjugation, but they can do something. Here about 30 seconds. Okay, so yeah, if you do this one here, and then you're gonna have, this is where you have alpha and beta position, right? So I'm gonna do. Okay, so can I move on? Okay. All right, so I'll do the same thing, but here what I'm gonna do the addition to this this type of a case is now RQ groups. So let's do RQ group addition with the same mechanism. Okay. And then in here, what you can try is the maybe let's say we have the same problem. Okay. And then here, I'm not gonna put the mean groups here. We're gonna put the Q groups over here. Unlike the other one, there's actually a very specific, unique reaction you can do is what we call, actually we learned diorganic copper. Do you guys remember this in Ogu 1? So we have diorganic copper. And then what do you remember they can actually replace one of the methyl group over here, but not on here, not on the carbonyl groups, not here. So they make, here, but they're gonna replace here and here. Okay. So if you treat this one with the diorganic copper, they form in the 1,4 alpha beta. So the diorganic copper, as we learned in Ogu 1, you just adding one R group to the compounds, but not on here in the carbonyl group because of the this alpha beta carbon saturation. So we're gonna actually put it on here in the beta carbon. That's the only difference we can do with this one. So let me give you one example more. You can try this one. And I'll change this one to bigger. Okay, let's make it bigger. Yeah. Let's try this one, maybe 1 or 2 minutes. Okay. So this, I would just remind you, so this is R2 copper, and you just need to edit only one. So we call this diorganic copper, but one R will be added to the compounds. But here in this situation, you're gonna put it on the better carbon. That's only the change we're gonna make for this one. Okay, 30 seconds or 20 seconds. All right, so yeah, let's do this together. So I'm gonna add this one R out of 2 here, not here. So, and then this double bond will be gone. Okay. This, oh yeah, and that one. Okay, let's try one more. Okay, try to find the alpha and beta carbon, and to the addition on 1 R from the diorganic copper to the beta carbon. That's it. And, oh, and remove the double bond just to trick, so you can. Okay, so yeah, let's do this together. And this is the position, but we have ethyl group line, so I'm gonna do this one. That's it. Okay, you guys got it right. All right, so that's it for chapter 19. So I'll finish it here today because we're done.